Now that we've talked about how to write chemical reactions and balance those equations, we're going to talk about the different types of reactions that there are. There's an example here, but we're just going to dive straight into the notes. There are different types of chemical reactions, and they can be classified as combination, which you'll also hear called synthesis. I personally prefer synthesis because then you don't have two that start out COMB and it's easier to distinguish them, but both are used. Decomposition, single replacement, double replacement, and combustion. I will say that sometimes these two are called displacement instead of replacement. Both work. And we're going to go through each of them here in just a moment, but I'll point out that if you do consider this one synthesis, then you have synthesis, decomposition, single replacement, double replacement, and combustion, and have really short 1 or 2 letter abbreviations for them. We unfortunately do have 2 S's and 2 D's, and so you do have to have the R there for the replacement ones, but still it's a shorter shortcut. We're going to get into explaining each of these on the coming slides. So the first one here is a combination reaction, as I've mentioned already, also known as synthesis, and it's one where you have 2 or more elements form one product, or it can be simple compounds that combine to form just one product. And so we have a generic reaction equation here where A and B are just any chemical, and you can see some examples down here, and they form a single product of A bonded to B, as you can see some examples of down here. To be clear, it doesn't mean that we have just one of each. In both these first examples here, we have 2 of A, and we happen to have B being not alone but bonded to itself. Most often it's just like this, where these are 2 or more elements, as it says here. The other one here is where we have simple compounds. Your elements one tend to form ionic compounds, and your simple compounds ones, they tend to be molecules that are covalently bonded to begin with, and we can get something on the other side that is ionic or covalent. To be clear as well, this is a little bit of an oversimplification. There's a famous reaction that occurs in all plants where they take carbon dioxide and water to turn it into sugar, specifically glucose, C6H12O6, and oxygen as part of the carbon dioxide oxygen cycle. This one happens to not be balanced, and I have seen this equation often enough that I have the coefficients memorized, but you of course could take a stab at balancing it on your own here before I move on. But this particular one, it's got the special condition of light above it, and you'll notice this is photosynthesis. Well, of course, you can hear within that synthesis the other name for combination reactions. How is this synthesis if we have 2 reactants but also 2 products? In reality, what matters is we start with lots of pieces. So here we have 6 and 6, or 12 pieces. And in the end, we end up with fewer pieces, 1 and 6, or 7 pieces. And so a synthesis reaction results in fewer pieces. And I'll be honest, I was taught synthesis. I'm going to frequently revert to saying synthesis. I'm not trying to cause confusion. It's just the way I was taught, and I do like the word better. One of those examples on the prior slide was this reaction. It's an absolutely awesome reaction, and this middle picture here does not do it justice. Back in early days of cameras, and if you've ever seen a movie or recreation where they use flash powder and they actually light powder when they go to take the photo, that flash powder was usually magnesium. Sparklers used to have magnesium. It's just incredibly bright white when it burns, and cameras have a hard time capturing it, but this here certainly does not do it justice. It looks to me like it's the end of the reaction. But we have magnesium here, and we actually have oxygen in the air. I don't know why they chose to wait until the second picture to show the oxygen in the air. I mean, yes, we start with magnesium here, and we start with oxygen here, and then when you add the heat, the energy to get this reaction going, that's where the reaction is taking place. And so you have magnesium and oxygen together. But to me, these two here belong on the before, on your reactant side. This here, this photo goes with the center here, and then this is your after, and you end up with something called magnesium oxide, and it's this repeating pattern of magnesiums and oxygens bonding together. We took magnesium and we combined it with oxygen to create magnesium oxide, and that is a synthesis reaction or combination reaction. Decomposition reaction, it's the opposite. Decomposition, you do always start with one piece and it becomes more pieces. You start with one thing and it breaks down into more things. A couple of examples there for you. Here is a photo of one of those. I've actually not done this because mercury itself is really toxic, and at least for high schools, it's illegal for me to have mercury in the high school. I don't know if that law is universal for all schools, but mercury is really beginning to be phased out because we just know how toxic it is. I have played with mercury earlier in my life, but I certainly would not do this kind of reaction where you have to add heat energy and start to vaporize that and breathe it in. I've mentioned the Mad Hatter story before. In a single replacement reaction, we have one element replace another in a compound. And so they swap places. Now, even though this one is written out as swapping with it, as it's ending up somewhere else, and that's not actually quite how they show it down here. I'll show you how I would write that here in just a moment. But even though in the reaction equation, they swap places and there's movement of both, the way I always describe it is that the first piece, A here, swaps with another piece and the other piece is just left over. And that is kind of what they're showing up here, that A comes in, replaces B, and so now you have A and C bonded together. That's the replacement there, that B has been replaced by C. But B isn't replacing A. A was just on its own to begin with, and now B is just kind of there, and it's around, but it's not actually replacing anything. There's nothing to replace, really, as the one piece is getting used up. Now, like I said, down here, they don't really show it that way. Here they show A and B, C, and then over here they show AC. They've really switched the order of things. A goes in and does replace B, but then they're writing AC first and B second. Order of reactants, order of products doesn't matter. There is a preferred way for some reactions. We're not going to worry about those, but they've written both of these down here as this. And by far, this is the most common type of single replacement reaction, where we have a metal replacing another metal, or more specifically, a cation, a positively charged piece, replacing another positively charged piece. There are single replacement reactions that involve anions, and when those happen, it's the same idea that one piece is replacing another, but if this was a non-metal or something that would become an anion, it's going to replace the anion there, and you would end up with C plus Ba. If we're being really picky, this one here is not AB because the anion always goes second. Anyway, that's single replacement. Over here is an example of one of those, zinc reacting with hydrochloric acid. This is a much better before-after picture here than that prior one that I was complaining about. But we have zinc and hydrochloric acid. The hydrochloric acid dissolves, so the pieces are separated. And then when we're done, we form hydrogen gas that bubbles away here. And so that's the other piece that's not truly being replaced. It's just out there afterwards, and then what's actually happened is the zinc has replaced the hydrogen in these, which is why we have the zinc around with the chloride ion dissolved in solution there. In double replacement reaction, we have the positive cations switch place with one another, and that's how they're showing it here, that A swaps with C and C swaps with A. Now here the double arrow does belong because we actually have two things trading places, and they've color coded down here, which is wonderful, but silver replaces the sodium and sodium replaces the silver, and then we end up with silver chloride and sodium nitrate. Though you'll notice once again they did swap the order of the products here the way that this one is written. There's nothing wrong with that, but you can view this as another kind of swap. Instead of it being positive ions, we can view it as the negative ions instead. It comes out exactly the same. You can try that with the first one, or I'll show it here on the second one, because that's not what they actually do. They don't color code it here, but if we take the sulfur and we replace the chlorine with that, and we take the chlorine and replace it with the sulfur, then we end up with zinc bonded to chlorine and hydrogen bonded to sulfur. It's the same thing. Whether you're swapping the positive pieces or the negative pieces, you're going to get a replacement. And this is the most common type of double replacement reaction, where we start out with this one up here, where we start out with something that is dissolved in both of our reactants, but then one of the products comes out, and that one is specifically called a precipitate. reaction. We also have double replacement reactions that involve producing a gas, and so instead of a solid sinking down through the solution, you have gases bubbling up through the solution that's left over, and of course the solution, and we have something dissolved. The thing that's there is mostly water. Lastly, there is another one that is acid-base reactions, and they were mentioned when we covered how to balance acid-base reactions. Those always start with an acid that has a hydrogen bonded to something and a base that is something bonded to a hydroxide, and then when they react, they produce water and a salt, something that is ionically bonded, that comes from those two pieces there. A lot of times these don't have a visible change unless we add in an extra special chemical called an indicator that forces it to have a visible change, but they are also a double replacement reaction. They're special cases of double replacement. This one here, they've given a different one than what's on the prior slide there, and so we have sodium sulfate and barium chloride, both of which are solutions and dissolve. So we have liquid here. There's also liquid in this dropper that's coming down, and it looks like we've got just a small stream flowing out there. And when those two meet, then we form a solid precipitate, this white cloudy stuff that's there, that's going to eventually settle down and sink to the bottom of the solution that we could then separate by pouring it through a filter. And the solution of sodium chloride, that is just regular old table salt that we formed here, will flow through the filter paper, and the barium sulfate solid is left in the filter paper. And this one here is one of those double replacement precipitate, which will be abbreviated as PPT there. The last type of reaction here that we have is a combustion reaction. And combustion reactions always are carbon-containing compounds. More specifically, they are usually hydrocarbons. That is, compounds that contain carbon and hydrogen, and sometimes other things. These here are both just simple hydrocarbons that only contain carbon and hydrogen, and they are burning in the presence of oxygen gas, which is O2. I don't know why they didn't take the time to write that one there like they did with the other two. The products are always carbon dioxide and water. If you have a complex hydrocarbon that has, say, sulfurs or nitrogens or oxygens in there, then it turns out that you get other oxides over here on the product side. That is, we end up with a carbon oxide, a hydrogen oxide. Water is a hydrogen oxide. If you have sulfur in there, then you get sulfur oxides. Nitrogen, you get nitrogen oxides. You'd have to be told which ones are formed because they're hard to predict which ones, because there's more than one sulfur and nitrogen oxide. We don't get oxygen oxides because, of course, that'd just be oxygen. And so there are some simple hydrocarbons or slightly complicated hydrocarbons that do have oxygens in there. Those oxygens just contribute to the available oxygens for producing the carbon dioxide and water. And there is always energy released in those combustion reactions. But combustion is just a fancy word for burning here, and usually they're starting with some kind of spark or trigger of heat to get them going. This one here is methane. It turns out you don't need to know that yet. If you take 111, we definitely get into that a lot. But methane is the gas that usually flows out of the Bunsen burners if you're live and we're doing labs like that. It's also the gas that is usually your natural gas to heat a home. The other common one for heating homes, especially if you're not close to the pipelines for those, is propane. And the other places propanes are used are propane grills, and a lot of campers or trailers will use propane heat for cooking and heating the camper instead of electricity, which is your other way that's commonly done. And there are other hydrocarbons. These, I will point out, they tend to get fairly large with our coefficients that it takes for balancing. Photosynthesis is, interestingly, if you go back in the video and look at that one, it's almost a reverse combustion reaction. We had carbon dioxide and water reacting to produce a sugar and oxygen, so we produced a hydrocarbon and oxygen. It's almost like it's a reverse combustion reaction, which is just always interested me, fascinated me. But combustion reactions always have these two products, and they always involve oxygen or a chemical that contains oxygen in it that's called an oxidizer. And so we'll always have oxygen or an oxidizer there. And that is what a combustion reaction will look like. They are the easiest to identify. Beyond that, I will point out a simple shortcut. If we're dealing with just the simplest ones, no exceptions, single replacements always have a plus sign on the reactant side. Decompositions have a plus sign on the product side. Replacement reactions have a plus sign on both sides, and the way you tell them apart is you have a single replacement if something is alone on both sides. You have a double replacement if everything is bonded, nothing's alone. And then combustion reactions, you always have oxygen, and you have carbon dioxide and water on your product side. So it does have a plus sign on both sides like the replacement reactions do, but it's really easy to identify because of the other things that are there. Again, just a shortcut to help you identify them. Certainly these definitions are the true way to go about identifying them. Health application here, if you have not enough oxygen for the burning process, then we can get something called incomplete combustion. And the thing is, oxygen is reactive enough that the process will still happen, we'll still get a burning, but because of incomplete combustion, we'll end up forming carbon monoxide. Well, carbon monoxide is a colorless, odorless, tasteless, I'll add in there, poisonous gas, and it ends up bonding to the hemoglobin in your blood. Hemoglobin is what transports the oxygen around to your cells, but the oxygen bonds weakly to the hemoglobin so that when it gets to the cells, it can release the oxygen for the reactions that occur within your cells for body processes to occur. Carbon monoxide bonds tightly to the hemoglobin, doesn't let go of it, and because of that, then you end up with the hemoglobin no longer being able to transport oxygen, and you end up essentially getting really tired and falling to sleep, and you don't wake up because the carbon monoxide poisoning. And here it has the specifics of what happens and some of the symptoms that you can have, and I have a story that I'm going to make you sit through here. I suppose you could fast forward a bit if you don't want to, but my mom has a friend who for Christmas got what everyone wants for Christmas, a carbon monoxide detector from her in-laws. It's a lame Christmas present. No one asked for that to be underneath the Christmas tree. They open it up, smile and say thank you, plug the batteries in, and the thing starts beeping immediately. And oh great, not only do we have a carbon monoxide detector, we have a broken one. And so they fiddle with it, and they try to mess with it later in the day, and they pop it back in, and it's still going off. And they thought to themselves for a moment, wait a second, what if this isn't a broken carbon monoxide detector and the worst Christmas gift ever? What if it is the most perfectly timed Christmas gift ever? And it turns out it was. The concentration of carbon monoxide in their house was high enough that they were not far from passing out and going to sleep and dying like that, unfortunately. And if we go back here a couple slides, it does mention that if you have these things, gas or oil burning stoves, any kind of wood stove or fireplace, I will add on to that an attached car garage. You should never run a car or any other kind of gasoline powered or other hydrocarbon powered, diesel, whatever, device, vehicle inside of a enclosed garage. But if that garage is attached to your house, it's all the more essential that you get yourself a carbon monoxide detector near all of those sources, and outside of the bedroom or bedrooms. It's recommended you have one on each floor. My parents had a gas water heater that went bad after just enough years, and it started to leak carbon monoxide. Their detector went off, and they had to call out the fire department. That's what you do if you have it. They tested it, and sure enough, there's carbon monoxide building up in the basement. And so then they closed off the gas, turned off the gas. They hired someone to come out and fix the furnace and fix the pipelines, an HVAC person, and everything's been fine since, of course. But please protect yourself. Downside of carbon monoxide detectors is they do have a limited amount of time that they last. They have a reaction that goes on inside them, and eventually the reaction essentially finishes. You run out of reactants, just like you run out of reactants to react inside of a battery. They go dead, and there's no way to refresh them. You just have to dispose of them and purchase a new one. They last about 7 years. Unfortunately, they'll sit on the shelf at the store a couple years before you get around to buying them, and so then they'll not last quite as long, but they are essential to have. Smoke detectors, on the other hand, as long as you keep fresh batteries in them, and of course you have to keep fresh batteries in your carbon monoxide detector, and it should test them regularly enough, but smoke detectors, they do last pretty much forever. They're they're going to last you plenty of time as long as you treat them well and keep replacing those batteries. But please protect yourself. I do care about you and don't want you to run into any of those kinds of problems. This one here is a table that summarizes the reactions. To be honest, it probably would have been more than enough, but you can see here the arrow thing that I was talking about just a moment ago with the arrows and the plus signs and how to tell them apart. As I mentioned, in single replacements, you always have something alone on both sides. In double replacements, everything is bonded on both sides of the reaction equation. You can check that over here as well. I won't take the time to go through all those. One thing I will point out here is that they have shown you a generic form for balancing simple hydrocarbon reactions. They have here, instead of numeric C subscripts, different variables, X and Y, and then a Z as a coefficient here. And it turns out that it is guaranteed that if you want to memorize this form, that will work for any simple hydrocarbon combustion. I personally have never memorized this one or cared to because it is hard to apply. It's a lot to remember, and I think it's easier just to guess and check your way there like you do with balancing any other reaction. And in addition to that, if you have one of those complex hydrocarbons that I was talking about that has oxygen in it or has sulfurs or nitrogens in it, this goes out the window. It's no longer useful for balancing, and so I just don't even worry about it. But sure enough, here in terms of identifying a combustion reaction, you have a hydrocarbon, oxygen, carbon dioxide, water. If it's a complex hydrocarbon, other oxide compounds out there, and you have this release of energy that always happens. Not to say that the other reactions don't release energy, it's just that this one here, it's always going to, so that's why it's mentioned. We've got a couple practices here over identifying types of reactions. So here we have plus signs on both sides, something alone on both sides. This is going to be a single replacement reaction. Nothing is alone on either side. In fact, I think this is one they used as an example earlier, but that one there is a double replacement reaction. Here we have, let's see here, something alone here and something alone there, plus signs on both sides. That's going to be a single replacement reaction. And then this one's simple. We have carbons and hydrogens, oxygen, carbon dioxide, and water. That is a combustion reaction. More practice over these before we wrap up the notes. This one here is a synthesis reaction or a combination. Here we have, again, something alone on both sides, so that's a single replacement reaction. Here we have the hydrocarbon, oxygen, carbon dioxide, and water, so that's a combustion reaction. Then we have something where nothing is alone on either side and plus signs on both sides. That is a double replacement reaction. And it looks like process elimination. We're going to have one of each of these here. And sure enough, one reactant that forms more products. That is a decomposition reaction. And that finishes up section 5.